swiftly now to Steve, who will be presenting on from his perspective. So Steve Holmes is just recently of Meta, formerly known as Facebook, a now fellow of the University of Glasgow, and more salient background or introductions I'll let him do for himself. So Steve, shall we try you sharing the screen and hope for slightly greater success?
Okay, thank you. We won't share the screen. There should be no need.
You said this to me the other day. My apologies. Yes, of course.
This is more of a radio broadcast than a television broadcast for me.
Good.
So thank you for the introduction. I won't waste anybody's time with continuing to introduce myself in any more detail. Neil, you're still showing as full screen on my screen. Can everybody see me as full screen on theirs? Yeah, okay.
Yep.
Well, now I can see myself full screen. That's horrible. Let's hide myself. Okay. So good afternoon. Anyway, I want to spend some time talking about the technology that almost certainly will be used in consumer augmented reality. I'm going to look at what an AR system needs to be, roughly how it's specified, some use cases, and a few of the ethical issues that are at least being considered in the industry currently. Something that is important to note that this version of AR needs to satisfy multiple extraordinarily challenging requirements. Neil's touched on a few of those, but hopefully I'll touch on a few more. Firstly, let's look at what this version, the version of AR that I'm going to talk about, needs to be. It must at first be compelling so that a potential user sees the value almost immediately and wants to buy in. Examples of this sort of compelling technology include the printing press, the television, the car, and more recently, smartphones. The headset will almost certainly need to be of a glasses form factor or close to that form factor. This is mostly because potential users expect this form factor. Obtrusive ski goggles or VR-like box on the head form factors are not likely to be acceptable. The earliest releases of AR glasses will also be paired with a secondary element, perhaps a linked smartphone or a separate puck worn on the body that will contain at least the main power source and the heavy lifting compute elements. There's a need for the headset to be high-end. That is, the whole system is to be well constructed from quality materials. It needs to be durable and with a high specification to ensure high capability and flexible operation for all potential users. The visual and audio elements will need to create convincing virtual objects with high fidelity. The user interface will need to be intuitive, smooth, and seamless. The headset itself will, as Neil suggested, need to be socially acceptable. This is a broad term that I've tended to interpret in this context as meaning that the user will at least not be generally ridiculed. The headset will need to somehow blend in. A useful AR system will also need to be conveniently all-day wearable, like conventional spectacles, say for 8 hours a day of every 24, with minimal discomfort and minimal downtime for in-day recharging. Finally, and obviously, a system aimed at consumers will need to be consumer-based. That is, there will need to be built-in enormous flexibility and hence large numbers of applications covering multiple possible uses, just like we have with the smartphone. So those are some of the basic requirements of an AR system. There are more. Now, simply to begin to address these issues, we require a system with a basic specification that is already hugely challenging. And in a little more detail, starting at the means to create the visual display, the near-to-eye display projector engine requires red, blue, and green light sources, methods for spatial and temporal modulation of the light source from those light sources, focusing optics, and some form of combiner optics to redirect the light into the eye whilst allowing the user to see the real world without noticeable obfuscation or distracting artifacts. There are many choices for the display engine architecture. Despite this, the constraints on the system designer are enormously challenging. There's no single obvious correct way to approach this challenge. A glasses form factor implies that the on-head part of the system has a similar weight and size as normal glasses. Most standard glasses weigh far less than 80 grams and have frames that are less than 5 millimeters thick. at their thickest. I personally own a lot of pairs of glasses, and my most extreme ones, let me show you these, go beyond this size limit. Interestingly, these don't go beyond the weight limit. They are over 10 millimeters at their thickest, but only weigh 56 grams. They do at least satisfy my low bar definition of social acceptability, since I have not been knowingly at least ridiculed whilst wearing them. Studies have shown that people struggle to wear glasses that weigh more than about 100 grams for even relatively short periods. So these size and weight constraints make self-contained AR glasses, with all of the requirements outlined earlier, utterly impossible with existing technology, hence the need for a separate paired element. The power demand now for the whole system will need to be sufficiently low such that the batteries will last a large fraction of 8 hours on a single charge. Users will not tolerate the need to search for charging points throughout their day. Battery technology is certainly progressing, but there are fundamental physical and chemical factors that limit the maximum energy density that a battery could ever contain. Power use within the system must be frugally managed. Thermal issues are also a problem, but perhaps beyond the scope here. Excuse me. Display brightness is key to a great experience. The system will need to be able to compete with the outdoor summer sun, say, in California. There are currently no aberration-free light sources that simultaneously provide the required brightness and modulation at sufficiently low power and that fit within the required form factor. Much of my team's time has been spent on this research over the past 5 years, with some significant progress, but the bar is set high. The system demands for real-time compute also is extreme, arguably beyond that required by high-resolution video gaming. The per-frame calculations within the graphics pipeline must be done obviously within frame time and account for the actual and the predicted movement of the user's head and potentially their eyes, whilst doing this all in full color and in 3 dimensions. It's a harder challenge than VR, since the control of the virtual world in VR is completely within the scope of the developer and hence their software. In VR, light sources are all virtual, and so their properties are fully predictable. Even so, it still remains challenging to account for all of the lighting nuances. In AR, the lighting intensity, color, and direction is dictated by the real world and must be measured by the headset and accurately accounted for within the graphics pipeline for virtual objects to appear as though they belong in the real world. Some of these notions lead to the concept of world locking. Many, although not necessarily all, visual objects projected into the user's field of view will need to remain stationary or move appropriately relative to the real world as the user moves. This is world locking. Objects are locked to the real world. This requires a system to reconstruct the virtual model of the real world and determine sets of fixed reference points in real time continuously. There is hence a need for the system to possess vision with depth perception. The simplest way to achieve this is to use at least 2 visible light or infrared wavelength video cameras. World locking is incidentally also required for the audio system. Virtual noise sources must be world locked too, although the positional accuracy of the virtual audio sources is much less demanding than that of a visible feature. The audio system will likely be of a behind the ears cartilage conduction design and will deliver the level of sound quality that we expect from high-end earbuds, whilst not obstructing real-world sounds. Moving on to AR field of view, that's the size of the visual field that the display needs to cover. Existing glasses wearers are aware that their in-focus field of view is limited by the frames of their glasses, although useful information can be gleaned from the extreme periphery region beyond the frame. AR typically aims to cover this same region, which typically is more than 90 degrees of the horizontal field. Related to this is display resolution, which must be high, at least within the region of the fovea. That is the most sensitive part of the retina. The published target resolution for a typical AR display is better than 1080p. That's the resolution of a standard HD TV, or these days a basic smartphone. This resolution is fairly impressive on a monitor covering typically 25 degrees of a viewer's field of view, but for great AR, the field of view will need to be over 90 degrees. This requires either foveation, that is higher resolution in the field of view covered by the fovea. This demands accurate and fast eye tracking, or much higher overall resolution than 1080p. A 1080p resolution covering a 90-degree field of view has a downside that the pixels become clearly visible. Much higher resolutions are required. No AR-compatible displays exist with either the required level of resolution within the footprint available for the display or the means to foveate that display. Moving now to color gamut. This is a complex measure of the range of colors available in a display and hence how precisely a display reproduces the colors of real-world objects. Users expect a wide color gamut with high color saturation. No display is perfect, and the ones being developed for AR purposes are beginning to approach minimum standards for normal displays used in smartphones. The color gamut will get better with time as the displays are developed. The specification for latency is also key. Latency in AR, VR is a measure of the delay between movements of the user's head and corresponding movements of world-locked virtual objects. When you move your head, you do not expect apparently stationary objects to jump about during the movement. Perception scientists have studied this and arrived at a latency time of less than a few milliseconds for human perception in low inertia and hence potentially fast-moving systems. In early VR systems, this was not such a problem, as the weight of the headset increased the inertia of the user's head, hence reducing the acceleration rate, allowing sufficient time to predict and to calculate the new per-frame positions of the objects within the user's field of view. In AR, the added inertia of the glasses form factor headset is negligible, and so latency becomes a serious issue, placing an increased demand on the compute part of the system. A related specification is frame rate. This is the number of still frames displayed per second. This must be high for the best experience. Frame rate in AR and VR can vary without the user being aware of this, but must be greater than about 60 frames per second most of the time. This is higher than most frame rates we experience on other platforms. The reason for the high frame rate requirement is the need to allow the perception of smooth motion of world-locked objects in the virtual display as the user's head moves. Target figures of 120 frames per second have been discussed. The demand on power, compute, and the graphics pipeline all increase non-linearly with frame rate. There are also a vast array of increasingly esoteric visual artifacts, such as the rainbow effect, pupil swim, the screen door effect, divergence accommodation mismatch, and many others. These all have target specifications based on user studies by perception scientists, and really are beyond the remit of this talk. There is a need for active dimming. That is the dimming of selected parts of the real-world visual field to allow virtual objects to become more visible in bright environments, or to simply highlight certain areas. The specification for dimming is complex and involves the absolute opacity and the variability of opacity of the dimmed area. It also involves the quality of the dimmed edge. Sharp-edged dimmed regions are much harder, may be impossible to achieve, than soft-edged dimmed regions. And it involves the resolution of the dimmed area. Highly resolved dimming is much more challenging than lower resolution. Finally, in this section is eye tracking, which I mentioned in passing earlier. The need for a system to know where the user is looking is essential for some display design types of foveated display, as I mentioned earlier. Eye tracking is also essential for some use cases that we will come to later. The specification for eye tracking includes a percentage figure of the proportion of the population for which the system works. Everyone's eye and eyelid shapes are different. Measurements of the movement of glints reflecting from the eyeball typically are used to calibrate the system per user, but some users are simply outside the capability of such a system. A wider specification includes angular accuracy, temporal accuracy, as the eye rapidly saccades, repeatability, and of course, power consumption. That covers many of the broad specification requirements, all of which the tech giants are researching. I haven't provided too many exact figures. There are at least two reasons why I'm not happy to provide exact figures. Firstly, Meta has a thing about confidentiality, justifiably. This is a multi-hundreds of billions of dollars potential business, and competition is a thing. And secondly, I'm not sure that this audience is truly interested in milliwatts, volts, amps, nits, the photopic response curve, LEDs, SLEDs, lasers, optical combiners, or even the relative merits of raster versus Lissajous scanning. If I'm wrong, then I need a longer talk. So let's move on to use cases. If all of this is achieved, What will this technology allow the user to experience? Well, one of the most compelling general use cases is the provision of superpowers. For example, users will have near infinite knowledge. They will have super memory, super eyesight, and super hearing. That you might never forget someone's name could be an extremely valuable superpower for some people, me for one. Imagine as you network your way around a social event or a business meeting, your AR glasses will discreetly advise you of the name of the person you're looking at. It may advise you of the last things you and they talked about, interests that you share, maybe where they went on holiday last, maybe how many children they have, what their children's ages and names are. It might warn you to steer the conversation away from difficult or painful topics. Imagine how useful that could be. During this same interaction, the system could automatically boost the volume of the speech of the person to whom you're talking, or maybe the person you're just looking at. This could be done by simultaneously removing background noise and by boosting the volume of the noise of interest using the integrated directional microphones. This would be a huge step forward for those of us who struggle to hear conversations in noisy environments. An AR system also would have access to the knowledge base available via the internet, and so to the superpower of access to almost all human knowledge would be available. Even a multilingual superpower is possible. Obviously, one way close to real-time language translation is possible now. AR is not quite a babelfish, but potentially two users would be able to talk to each other face-to-face in real or in the real or the virtual world, almost in real time, each in their own native tongues, without knowledge of the other's language. The superpower of magnified vision is relatively simple to provide. It's almost trivial in the system that I've so far described. A magnified view from one of the cameras would simply pop up on demand in the user's eye line. Many other superpowers could be imagined, but what other use cases are there? Another clear use case is telepresence. That is the ability to socialize with other people on the same platform remotely. This is something we've all become increasingly familiar with during the current pandemic. The use of video telephony has become commonplace, but we all understand its limitations as a means of communication. In the AR world, this interaction with friends and family would be in 3D. It would allow users to move around. It would be possible to share in real time virtual objects, photos, videos, or play virtual games, as though the other people were with you. Your friends or family's avatars would join you seamlessly in your environment and your avatar in theirs. Facial expressions and gestures would be captured and replicated via the avatars to ensure that the experience will be richer and more engaging than the current existing options. The business telepresence use case is clear too. Traveling to business meetings would become unusual, maybe should become unusual, rather than the default. Sharing ideas in AR is much easier than it is with existing platforms. An infinite number of virtual whiteboards will delight some users. Another, perhaps less obvious use case is the emulation of existing technology. Virtual technology might become the norm, at least for a while, as we get used to not carrying around our tech. AR will, of course, be able to project into the real world a virtual smartphone, a tablet, laptop, monitor, or even something some people still use called a television. We could interact with these pieces of virtual technology in exactly the same way as we do with our existing tech. You could, say, interact with the internet directly through the AR headset with gestures and voice commands, or perhaps, more familiarly, by clicking on the virtual buttons of a virtual tablet floating in front of you, apparently in the real world. The final use case that I want to briefly talk about is the context-aware personal assistant. This is potentially an application that is aware of the user's location, preferences, and interests, and potentially of those of the people that the system detects are with you, either physically or virtually. It would gain some of these insights from search histories or from previous occasions when it has offered suggestions relevant to the present circumstances, and the user has either been interested or has moved on to something deemed more interesting. So, for example, as you're physically walking in a new location, the assistant might offer insights into local history or the nearby architecture. It might suggest visits to bars, restaurants, coffee shops, museums, theatres, or music venues as appropriate to your preferences and to the time of day, potentially even taking into account the preferences of the people you're with and to your recent conversations with them. It might arrive at suggestions that sit within the intersection of the current needs and preferences of the group. The possibilities are boundless. Many other use cases exist for the consumer, but I want to briefly touch on some of the many use cases this technology could provide for the platform developer and the suppliers wishing to advertise on the platform. The first use case that the platform will likely be used for is focused advertising. The idea that a user-oriented, context-aware advert for goods and/or services could be superimposed on the real world directly in the eye line of a user is almost thrilling for a supplier wishing to market their product. Direct selling follows almost immediately from focused advertising. A user would be able to purchase the context-sensitive advertised goods or services with a simple gesture. This could be a huge benefit for some users. It's not hard to imagine that when, say, one is looking at the train times on the boards at a mainline station, that ticket prices would appear in front of you with an immediate option to purchase and jump on the train with an automatically validated ticket. The final use case in this category that I want to quickly consider is access to users' data. Users' data is the key to unlock precisely directed, laser-focused advertising. The richness of the available data from an AR headset is orders of magnitude greater than that currently available via, for example, our current social media interactions. The value of that data is impossible to accurately estimate. The uses to which it could be put are frighteningly varied. Some might be beneficial, but others will be potentially highly dangerous. A simple benefit might be that the user will never need to see another advert for something that they have recently purchased. I find this silliness personally mildly irritating. Say as you search for and purchase a fridge online currently, you will see adverts for fridges for months after your new fridge has been delivered. In the world of AR, the headset can see that the fridge has been ordered and indeed delivered. So there's no value in wasting costly advertising space on fridges for that user, at least for a few years. So I want to move from use cases to the ethical issues that some of the capabilities and the use cases potentially create. I'll touch on one or two possible solutions. Privacy violation is an obvious area to consider. Constant video and audio recording with real-time uploading clearly violates other people's privacy in places where they might reasonably expect privacy. The Ray-Ban Stories solution to this issue is to place a small red LED on the frame of the glasses to indicate that the system is recording video. This indicator may not be fully understood by the people being recorded and can be easily defeated. In most countries and circumstances, people have no right to expect privacy when in public places. This seems to be an almost a priori truth. There have been recent changes in legislation in the UK to protect the privacy of some people in public and their activities. For example, non-consensual photography of women breastfeeding will soon specifically be an offence. The practice of upskirting already is. The notion of what privacy is comes into question when a system is as capable as AR will become. AR systems will be able to identify people and timestamp the moment and place of that identification. I expect to be and don't have a problem with being photographed when I am in public, not because I have an inflated view of my celebrity status, but because we are almost continuously surveilled in towns and cities across the UK by CCTV systems. I think, though, I would feel somewhat aggrieved if my identity and my location was available to whoever wished to know or wished to pay to know. We may not have the right to privacy when in public, but surely we have the right to anonymity. Largely, though, it is true that reasonable photography in public is not prohibited, nor is the overhearing of private conversations in public. A system that passes as a pair of glasses but is able to covertly amplify a conversation whilst continuously videoing those people without their knowledge or permission is, for me at least, pushing the ethical boundaries. There are more insidious privacy violations possible with an AR headset. The headset will be tracking the user's gaze direction and pupil dilation during the eye tracking, using the eye tracking system, and will be aware of what the user is looking at via the cameras. It will be able to determine some user preferences based on analysis of potentially long histories and patterns of dilation and eye dwell times. Might an AR system in the extreme be able to determine a user's sexual orientation even before the user is fully aware themselves? There are studies in the literature that demonstrate that there are measurable effects here and so potential ethical issues. The AR system will also track position in space and motion with high levels of precision. By using the GPS system, built-in gyroscopes and its cameras, the AR system will know how a user is walking and could potentially diagnose asymmetric, musculoskeletal issues long before the user is aware. This is obviously a benefit unless the information is accessible by a medical insurance company before it is accessible by the user's medical professionals. The potential for other privacy violations is enormous, but there are many other issues. For example, due to the nature of the rendering of surfaces in AR, there is a difficulty with dark objects rendered against a light real-world background. Neil touched on this earlier. In all cases, virtual objects in AR are to some degree transparent. At the extreme, black is rendered as totally transparent, regardless of the quality of the real-world background. Granted, in many situations of darker virtual objects rendered against lighter real-world background, the brain will fill in the details and perceive the expected opaque surface. Unfortunately, there is a limit to the brain's ability to do this. And, for example, dark human skin tones are rendered and perceived as close to transparent, unless a mitigating strategy is applied. This leads to a few disquieting possibilities. Firstly, people with dark skin tones might be required to select a skin tone for their AR avatar that is lighter than their own. The system could do this automatically without the user's intervention, but who chooses the limiting cases? And how could anyone think this is acceptable? The second option might be to use a locally dimmed background behind the avatar. This has been shown to work for even extremely dark skin tones. But in my view, it must be done for all avatars. This would avoid the possibility of categorizing people into groups such as people with dimmed avatars and people without. Othering cannot, must not be the default position. There's a more general point here about inventing solutions that work well for the extreme cases and not just the mean and a few standard deviations from the mean. Here, the extreme cases might be albino skin tones at one end and extreme dark skin tones at the other. If the system works for both of these cases, then it will work for everyone. The use cases of focused advertising and direct selling seem similar to the current smartphone or tablet experience, but the AR world is more compelling and more immediate. The user is expected to be in this AR world almost continuously during the day, and so the ability of suppliers to get their message seamlessly into the user's world in a focused way and in context is greatly magnified. Will those suppliers all have our best interests in mind? Will they not ensure that their adverts appear in the most appropriate places at the most appropriate times? And indeed, what is appropriate for the advertiser may not align with that which is appropriate for the user. Potential dangers exist in the heightened ability for lobby groups to push their agendas towards vulnerable people, and hence into increasingly narrow echo chambers or further down their rabbit holes. The way this ability might be policed internationally is not clear. The social media platforms will try to ensure that this danger is minimized, but their track record here does not inspire confidence. In conclusion, I hope that I've provided a high-level overview of the technology that AR will use and what that technology might ultimately facilitate. One of the important takeaways is that the technology is not ready for consumer-level AR. Several of the largest tech companies on the planet have been aggressively driving towards this goal, building teams of the best scientists, engineers, and managers on the planet. They've been doing this for close to a decade, and there is still no clear route to provide the richness of experience in AR that has been promised. Based on the existing technology in 2022, it is certainly true to state that visible virtual objects are unlikely to be confused in the mind of any user with real objects, at least for the foreseeable future. Another critical takeaway is that we do not know how this technology will develop, to what uses it will be put, nor do we know much about, if anything, about the control measures that are possible to apply in this space. We do have time to consider the deeper philosophical issues. Thank you for your time.